All right, let's begin chapter 5. This is the last full chapter. And then chapter 6 only has one or two sections, so pretty sure. We talked about in chapter 2, section 3, we talk about composite functions or composition of functions. Those were functions within functions. Okay, that's going to be important for us to prove if inverse functions really exist. What are inverse functions? Let's look at first the word inverse. To find the inverse, change the first and second coordinates of each ordered pair. In a relation. That sounds mathematical. So an ordered pair is XY. To find the inverse of it, just switch X and Y. That's what it's just telling you. A relation is just that. It's how one ordered pair or one function fits into another one, or what ordered pair fits into another. So for example, if we had a function h of x, and it was comprised of these ordered pairs. These are the points in the function. The inverse of h of x would be this. First, we have to use, how do we distinguish whether it's a regular function or an inverse function? We use that notation, a -1 exponent. When you see that, then you know that that function is an inverse. So if I give you these ordered pairs, the inverse would be just switch the x and y's. If it was 1, 2 in the first one, the inverse would be 2, 1. Next would be 4, 3. Then 6, 5. Then 8, 7. So all you do is switch the x and the y. Example 1. G is comprised of these points: 2, 4, -1, 3, -2, 0. Find the inverse and graph it. So what would the inverse be? Four, two. Very good. Excellent. Now we have to graph it. So we just switch the X and Y's, and now we have to graph it. So for G, I'm going to use dots, and for the inverse, I'm going to use plus marks. All right, so the first point we had was at 2, 4. Then -1, 3. Then -2, 0. That was our original function. Now the inverse function, we had the points 4, 2. 3, -1. And then 0, -2. There aren't enough points, but there's a definite pattern. It's a reflection across the origin, across the line y equals x. So yeah, that's exactly what it is. It's a mirror image. Example 2. Find the equation for the inverse of the relation. Find the equation. Okay, here are the steps. To find the inverse, here are my steps. Change x and y. And then solve for y. That will be your inverse. So the first thing we have to do with our equation is switch x and y. This is step 1. Nope, just change x and y, because we're finding the equation of the inverse, not the graph of it. That's how we would graph it. We'd graph the first function and then just switch all the points. Okay, we see that we can't solve because the only thing we can do here is we can factor out a y. That gives us, so we can't solve for y. So this one has no inverse for y for that function. Let's look at this example. Find the inverse. Okay, I should say no inverse for y because we can't solve for y. We can't get y to have only one answer.
One is X minus two.
Let's see. So we switch x and y. Subtract 2 from both sides. And divide by 5. So y inverse equals 1 over 5x minus 2 over 5. Very good.
Well, I really want to ask about the infinity. So I was thinking about it with the inequalities.
Mhm.
How would that look like in an equation?
You don't, these already are infinite numbers because what's the domain of this equation? What's the domain of this one? So yeah, so it automatically goes to infinity. The domain is already infinity. I'm glad you said that because if if the inverse exists, then the domain is defined. So like this one here, the domain of this one is infinity, the negative infinity, but since the inverse doesn't exist, it doesn't have a domain because this one would be a parabola, this one would be a hyperbola. It's not a function. Don't have inverses. Let's do one more. Y is equal to 3x minus 4 over 5. Find the inverse.
6, 4, 5, 3, X. Goes 4.
See. Yeah, so first you do switch X and Y. Then we get rid of the denominator, so we multiply both sides by 5. That cancels that. So 5x equals 3y minus 4. Get rid of the 4, add 4 to both sides, and divide by 3. So the inverse is 5 over 3x plus 4 over 3. So to go with your last question, we have to discuss something called one-to-one. One-to-oneness. But these are one-to-one functions. Oop, we have to see functions. A one-to-one function simply means if same inputs give same outputs and different inputs give different outputs. Then the function is one-to-one, which we abbreviate it this way. So instead of writing one-to-one, we just use this symbol here. So a function is one-to-one if for every input we have, we get the same output. In English, what that means now is if you have the same X value, then the Y values must be the same. To be one-to-one. If you have the same X values, then the Y values have to be the same. If you have different X values, then the Y values have to be different. So here's how it would look mathematically. If A equals B, then f of A equals f of B. If A does not equal B, then f of A does not equal f of B. That's what it says. And there's an easy test we can do to see this. So let's look at the properties of one-to-oneness. Of one to oneness. If f of x is 1-to-1, then its inverse is 1-to-1. The domain of f of x is the range of the inverse. And just the opposite. The range of the function is the domain of the inverse. And the last one. If f of x is an increasing function, then the inverse is a decreasing function.
Inverse also be parallel.
No. Because remember, you switch the points x and y. So it can't be inverse. Well, let's try it. Let's just pick some points. -5, 1. -4, 2. -3, 3. -2, 4. -5, 1. Or 0, 1. 0, 5. Let's see. Well, yeah, if it's a straight line, it has to, because it's reflected about the origin. But that only works for linear equations. Linear equations that are not crossed through the origin. Because this would be, instead of 0, 5, it would be 5, 0. At -1, 4, it'd be 4, -1. Maybe. We have to test those out. Well, no, because it's like the fourth one says, if f of x is increasing, if this graph is increasing, then the inverse is a decreasing function. That's what it would look like. We'll try to, I mean, plot some points, find a line, and then plot points, and then take the inverse of those points and see if that works. Example 3. Given the function f described by f of x equals 2x minus 3, prove that f is 1 to 1. The way you test it, or actually there are two ways to test it. And the first way we'll do it algebraically. If the inverse exists, then f of x is 1 to 1. As long as the inverse is a function. Remember, a function has to pass the vertical line test. So y equals 2x minus 3. To find the inverse, switch x and y and solve for y. So the inverse is 1 over 2x plus 3 over 2. Is this a function? Yes, it's linear. So f of x is 1 to 1. So basically all linear equations have inverses. Look at example 4. Given the function g of x equals x squared, prove g of x is not 1 to 1. How do we do that? Well, does this one have an inverse? Let's see. First off, switch X and Y and solve for Y. Okay, it's got an inverse. But is it a function? How do we define a function? Has to pass the vertical line test. Well, this one, for any Y value, or for any X value, there are two Y values. So I could put, if I put 4 inside here, if X equals 4, what does Y equal? Plus minus 2. So if X is 4, it has two Y values. It fails the vertical line test. So G of X, since the inverse doesn't exist, is not 1-to-1. Because remember, for every input, you have to have the same output. But here we have two different outputs for the same input. So that's one test to see if it's 1-to-1. We'll do another one in a second. The horizontal line test. If a horizontal line crosses the graph of a function more than once, the function is not 1-to-1. And since it's not 1-to-1, and its inverse is not a function. If a horizontal line crosses the graph more than once, the function is not 1-to-1. Because there are two inputs for the same output. And its inverse is not a function. I mean, we found the inverse, it's just it's not a function. Why not? Why is it not a function? Well, if we had this x squared and we found the inverse, we found this one. That's the inverse. It's not a function because it fails the vertical line test. We know it's not 1-to-1 because it fails the horizontal line test. So not 1-to-1. Here's some pictures. Well, example 5. A, f of x equals 4 minus x. It's asking here for the graph of the function, determine whether the function is one-to-one. Is that one-to-one? What's the graph going to look like? It crosses at 4, down 1/1. Does it pass the horizontal line test? Yeah, it only crosses the graph once. So it's one-to-one, which means that it has an inverse. And the inverse is a function.
Definition of the function.
If it's gonna, yeah, simply by, like this one here, by looking at the graph of the function. If it fails the horizontal line test, it's don't even waste your time with an inverse. It doesn't exist. Well, it'll exist, but it's not a function and it's not one-to-one, so it doesn't matter. C, f of x equals the cube root of x plus 2 plus 3. What is this graph going to look like? What's the basic function? Cube root of x. And the cube root of x looks like that. What does this do? It goes 2 units to the left and then 4 units up. So there's my new origin. Huh? This one? Oh, it's 3, I'm sorry, it's whatever, that's 3 units up. So we got 3 units. So the graph is like this. Is it one-to-one? Why? It passes for one-to-one, we use the horizontal line test. Yeah. And you can use it because it passes the vertical line test. It's a function, which means that there aren't 2 x's to the same y. So, but the horizontal line test proves that it's one-to-one, which means it has an inverse. It has an inverse that's also a function. Well, let's see what the inverse of this one would be. Let's find the inverse of this one. So it's y equals cube root of x plus 2 plus 3. First step, change x and y. So what's my next step? cube both sides. Very good. Those would cancel. So we have x minus 3 cubed equals y plus 2. So the y inverse, x minus 3 cubed minus 2. So what would that graph look like? Well, but what's the basic function? X cubed. And the x cubed looks like that. So you have to know what the basic function looks like first. Yeah, with the shifting is no problem. But what are you shifting? What kind of thing are you shifting? Yeah, now we know what the graph looks like. It shifts right 3 and down 2. So it's to the right 3 and down 2. So we have our origin right here. And so our graph looks like this. It's a mirror image of that, where it's supposed to be. Because if you just fold your paper, you have it. And then d f of x equals 3x to the 5th minus 20x cubed. So what do we know about this graph? Do we know the y-intercept? Yeah, it doesn't have a number here, so it's origin. Do we know the x-intercepts? Can we factor this out? Yeah, what do they both have in common? Leaving us with 3x squared minus 20. So we have 1, 0 at x cubed equals 0. So x equals 0. Check. And then solve this one. Three x squared equals positive 20. 20 over 3. Square root both sides. So x equals plus or minus 20 over 3. So here's positive 20 over 3, and here's negative 20 over 3. What do we know about the shape of the curve? Well, it's an odd degree, so they go opposite directions. And it's positive, so this side goes up, this side goes down. The multiplicities are odd, so we know they cross at all these places. So it'll look something like this. So is this function 1-to-1? Yeah, but it failed the horizontal line test at multiple points. So it doesn't have an inverse. That's a function. Yeah, so use the stuff that we've been taught already. So we can factor this out. We got x cubed here. So set both of them equal to 0. Solve for x. Those are your x-intercepts. You know the y-intercept. You know the multiplicities. I mean, if it's odd, it crosses. If it's even, it bounces. Let's look at the next example. Example 6. Determine whether is f of x 1-to-1. If so, find the inverse. Is it 1-to-1? How do we know? Because it's linear, and all linear equations pass the horizontal line test, and so it is 1-to-1. So let's find the inverse. First step, switch x and y. And solve for y.
How did you get the money after that? Because I thought two divided by two is one.
Okay, so we have x plus 3/2 equals y. So it's x over 2. What's the coefficient of x? So that's the same as 1/2 times x. That is one of the most, because we have to know what the slope is. That's the slope, up 1/2. A lot of people forget that there's a 1 there. So when I ask them what's the slope, they say 2. No, it's 1/2. Guys, I'm glad you asked that question. So it is 1-to-1. F of x is 1-to-1, and the inverse is equal to 1/2x plus 3/2. Example 7. Graph the two functions that we just did. X plus 3/2. Which, because it's a monomial, we can split them up. And we know that our slope is 1/2 and our y-intercept is 3/2. So the y-intercept is -3. Slope is 2/1. So up 2/1. So we have 1/2 x plus 1 and 1/2. So 1 and 1/2 is there. Up 1 over 2. It's symmetric about the line y equals x. So there's that equation. Example. Any questions so far? But again, if the function gets to be more difficult, then once you find the points of the first one, just change the x and y components and you'll find the inverse graph. This one. There's the original function, negative through this, the arrow pointing to this line. Example 8. Consider g of x equals x cubed plus 2. Is g of x 1 to 1? If so, find the inverse. And then graph them. All right, let's look at these. Is g of x 1 to 1? What does the graph look like? Yes, x cubed. We just shift up 2 spaces. So it starts here. And it goes up. And it goes down. So that's the x cubed. So it is 1 to 1 because it passes the horizontal line test. So let's find the inverse. So we have y cubed plus 2 equals x. Subtract 2. To get rid of that, we cube root both sides. So my inverse function is the cube root of x minus 2. The cube function looks like this. It's just shifted to the right 2 spaces. And there's the symmetric line. That's G inverse, and that's G. So we know since The original function is 1-to-1. We know the inverse is 1-to-1. So that we look at these looking at the graphs. What if we didn't have the graph? Proving the inverse exists algebraically. We're going to be using composite functions here. Because all of these equations we've had so far are pretty easy. But if we had some more complex, ugly ones, and we found the inverse of them, how do we know it's truly the inverse? So if f of x is a function and f inverse is its inverse, if that's true, if it's truly its inverse, then this has to be true also. F of f inverse of x has to equal x, and the f inverse of f of x also has to equal x. Let's look at the last one we just did. We had g of x is x cubed plus 2, and the inverse was the cube root of x minus 2. Let's do the g inverse first, the GOG. What this says is this equation goes in place of x. So the cube and cube root cancel, so we're left with x minus 2 plus 2. The 2's cancel, so it equals x. Check. Then we have to do it the other direction. We take the g function and put it in place of the x. So it's x cubed plus 2. Inside there, it's minus 2. The 2's cancel, so we're left with cube root of x cubed equals x. So those are inverses. We don't have to draw the graph. We just do this algebraically, the composite functions. Let's look at an easier one. Example 9. F of x is equal to 5x plus 8. And they're alleging that the inverse function is x minus 8 over 5. Is that its true inverse? True. So the way we prove it is by taking the composite functions of both of them. So we have the f inverse of f. Take this inverse function, plug it in place of f. First thing, the 5's cancel. That leaves x minus 8 plus 8. Then the 8's cancel, leaves us x. Check. Then the second test, we take the f of x function, plug it in place of x in the f inverse. So it's 5x plus 8 minus 8 over 5. There are possibilities, they do exist. I haven't seen any, but that's why you test them both. Yes, that's some great questions. So the 8's cancel, giving us 5x over 5. Check. So far so good. So we don't have to draw the graphs. We can just find the inverse and plug them into the composite function, see what works. What was that first one? This last part of this first section says that even if a function is not one-to-one, we can make it one-to-one. So if a function is not one-to-one, we can make it one-to-one by changing its domain. By changing, actually, it restricting. We're not changing it, we're just not taking it from negative infinity to positive infinity. Actually, the question we had earlier was this one. Is that function one-to-one? No, because if we switch x and y, then the inverse fails the horizontal line test. not one-to-one on the domain of negative infinity, positive infinity. But if we restrict the domain to 0 to infinity, only the positive ones, then F inverse is 1-to-1. So that's what the last part says. You can make it 1-to-1 by changing restricting the domain so it does work. All right. Any questions? No, you do restrict it. You can restrict whatever you want.